Hey pre-calculus friends, we are in section 6.8 and we are going to be talking about trigonometric inverses and their graphs. Our only bit of information that we want to make sure and be comfortable with is the concept of principal values. And if you think about, as I have drawn here, some of these functions that we're talking about, right? Sine and cosine and tangent here, what you can realize is that these functions are not one-to-one. And why is one-to-one important? Well, you remember that when we talk about inverse functions, they have to have the quality of being one-to-one. So we have discussed in the past functions that may look something like this. And we know that there's one, for every one x, there's one y. And we know that when we have an inverse function, that function will reflect over the y equals x line. So this function has its inverse. I could draw its inverse like that, right? The one-to-one piece is what's most important here. None of these functions that we've been discussing are one-to-one. And so when we deal with the trigonometric functions, we need to consider principal values. For instance, if I were to do the inverse sine of, let's say, 1/2, I'm only going to get one answer, though 1/2 sine will equal 1/2 infinitely many times along curve. And similarly for any value, if we were taking the inverse value of any tangent or cosine or secant or cotangent or anything, we know that we see those values infinitely many times. So we need to be educated or reminded or decide on principal values, values that are a part of the domain of the sine, cosine, and tangent functions that we'll use as we discuss its inverse. So what I want you to see here is that here we have a sine function. We know that the ordered pair is x times the sine of x, right? X and then the sine of x, so x and y. But when we deal with the inverse, we use arcsine, or sometimes we'll use this symbol, and we'll see it a little bit later on. We'll use sine inverse of x, okay? So we'll use that -1, which we know when we put that on a function, we're talking about the inverse function. But both arcsine and sine inverse x are both ways of talking about the sine function when, or the inverse function when we have sine of x as the x value, or the y value is now the x value and the x value is the y value. You guys get what I'm saying? And so what I want you to see here is this highlighted part that's in blue. This highlighted part, it goes from -pi/2 to pi/2, and that's the part that we really talk about inversing when we use a calculator or when we really consider the inverse function. So to go along with that, what our text and what, not just our text, but what we refer to this little blue part as is y equals the capital sine of x. So capital sine of x is only a portion of the sine function. It's the sine function from -pi/2 to pi/2. It's the sine function where we can see all of the possible values. It is a one-to-one function where we can comfortably talk about the inverse. The inverse function here would be y equals the arc. Look at my capital A, arcsine of x, or we can call it y is equal to the sine inverse. Notice the capital S of x. So all of these are reference to, well, both of these are reference to this blue section, and this y equals the capital sine of x is reference to this blue section. If you notice that the domain or the principal values that we're going to be talking about for the sine function are going to be from -1 up to, well, not actually, no. The principal values that we're going to talk about for y is equal to capital sine are going to be the domain where we have -pi/2 up to pi/2. And I'm going to write that in parenthetical notation like that. And so we have those values. I guess -pi/2 and pi/2 would be included. All right. So we are going to similarly do that for each of these. We'll similarly do that for cosine and tangent as well. So if you look at cosine, instead of going from -pi/2 to pi/2, we're going from 0 to pi, because we are from 0 to pi, we can travel through all the possible values of that cosine function. So this is y capital cosine there. Here, this is y arc cosine here, just in blue, or of course we can write that as y is equal to inverse cosine, capital, of course, cosine of x, and that's what's happening here. And so notice what our domain is here. Our domain of capital cosine goes from 0 to pi, and the range is still 1 to -1, and therefore the domain of the inverse is going to be going from -1 to 1. When we're dealing with the tangent, capital tan just refers to this one portion here that kind of exemplifies all the possible values of tangent. Again, when we are dealing with the inverse, we're dealing with that portion of the function because we can then have a one-to-one relationship. Y is equal to the tan inverse capital tangent of x, and we can see that all real numbers would be the domain here, whereas the range is going to go from -pi/2 to pi/2, but not including. All right. And here we just have a little blurb from the textbook that's kind of summarizing what we just talked about, which is the fact that when you have y equals capital sine of x, the inverse is going to be written in these two ways. Similarly, capital cosine, this is how you'd write the inverse. Capital tangent, the inverse is written there. And so again, we have another summary chart of the information that we just kind of went through as well here. And you know, I would suggest taking a screenshot. Let me get all this nonsense off here. Taking a screenshot of it, holding it, adding it to your notes, whatever makes it simple for you to keep in mind, I would do that, because you want to have a good idea of the domain and range of each of these functions. Okay, so here for example 1, we are asked to write the equation of the inverse of the arc y equals arctan 2x. Notice that we're dealing with the capital A here, so we are dealing with that truncated function where we're only considering a portion of the typical tangent and the arctan graph. Okay, so when we do inverses, we remember we have to switch the y and the x and then solve for the y in its new position. So x is equal to arctan 2y, and now we need to solve for y. So basically that means taking the tangent of x to undo what's happening here, and that being equal to 2y. At this point, we solve for y by, I'm going to just write the y on the left side, is equal to 1/2 the tangent capital T of x. And the two things that we were asked to do is to find the graph of this function that we created and this original function. And I'll be honest, I was trying to figure out how the text came up with their answer, and they truncated their graph, and I think it has to do with an oversight that I'm having right now with thinking about how the domain of one affects the domain of the other. But I'm going to give you the answer that I have, and so I'm going to graph actually both of these answers onto the same pair of coordinate axes. So setting up this first graph to graph y equals 1/2 tangent of x capital T, we know that we're going to be dealing with this function has its domain from -pi/2 to pi/2, and we're going to be graphing the tangent function, which goes up this way and then comes back down this way. So at pi/4, we're usually at 1 with the tangent function, but this is 1/2 the tangent of x. So the tangent of pi/4, which is usually 1, when I multiply by 1/2, will be down at 1/2. And similarly, we get the same thing for -pi/4, which would be here. So this gives us kind of a shape of the graph doing something like that, and then it's tangent over there, and then it goes back like this, and then it becomes, tangent's not the right word, it gets asymptotic as we get to those other values there. Now in the text, they just truncated the function where those two dots are, right here and right here, and I kind of don't get exactly why. I have a feeling again that it has to do with the data around the changing the domain of one and the function of the other, but I can't explain it well. So this is what I would expect for us to get. This is what I got. Every time I think about it, this is what I get. So I'm going to hold on to this unless you guys can explain it to me differently and see a different reason why you would get something else. But the graph of the of this guy here of arctangent is going to be reflected over the y equals x line. And so we get this this purple line here, and again the textbook had it truncated right at this point, And like I said, I'm not seeing the real reason why, but if you guys have some insight, I would love to hear it. So this is the graph that I would get given those directions. All right, so let's look at example 2, and we're going to find each of the following values. We're looking for the capital arc sine of negative square root of 2 over 2. So if we're thinking about the sine function, in a sense, we're thinking about when is the capital sine function, sine of x, equal to negative the square root of 2 over 2. We remember that the domain for this value, this x value, can go from negative pi over 2 all the way up to pi over 2, right? And so what value within this particular space is going to give me negative root 2 over 2? You remember the chart that we've talked about memorizing? We've talked about looking at some of those core values of sine, cosine, and tangent. This is why, because we know that a 45-degree angle is going to give me that, but a 45-degree angle will give me positive square root 2 over 2. We want negative square root of 2. So we would need a negative 45 or negative pi over 4. So in this case, x is going to have to be equal to negative pi over 4. Just to get a quick visual on this, I have the unit circle here, and we're looking at angles that are opening up this way up to pi over 2, and angles that are open down this way from negative pi over 2. And so here's pi over 4, where we get the sine value of the square root of 2 over 2. But when we are dealing with the capital sine, we're only dealing with stuff that's in basically the first quadrant and the fourth quadrant. We remember sine is positive in this quadrant and negative in this quadrant, and this is where we're focusing our attention, and because of that we need the negative pi over 4. I hope that makes sense. Hopefully that makes sense. Let's go ahead and take a look at this section here. So we're looking at the sine of the inverse sine of the cosine of pi over 2. And just like with order of operations, we want to do what's inside the parentheses first. What's the cosine of pi over 2? If you remember that, you'll know that if we're dealing with the cosine, I do like the unit circle, but if you're dealing with the cosine of 90 degrees is going to be 0. So if the cosine is 0, then what we're asking here is the inverse sine of what is going to give me 0. Now, what we're saying is, again, sine of what angle is going to equal 0. So what value? Again, we're still dealing with sine, so we're still dealing with negative pi over 2 to pi over 2 as the domain, right? What value of pi between these two values is going to give me 0 as the sine value? And that's going to be 0, because we know that the sine of 0 is 0. Again, this part of the problem is really taking on, like, just from the ideas that we know about from dealing with that little chart that we've worked on before, the inverse tan of 1. So basically what angle is going to give me, when I take the tangent of it, is going to give me 1, and we know that to be pi over 4. And then we can ask the same question, what angle when I take the sine of it is going to give me 1, and we know that to be pi over 2. When I subtract those two values, I'm going to get a negative pi over 4. And basically I'm taking the sine of negative pi over 4. So negative pi over 4 brings us to the fourth quadrant, and we know that the sine is going to be negative the square root of 2 over 2, as the sine of pi over 4 is square root of 2 over 2, but bringing it into the fourth quadrant, we know sine is negative. And let's check out this little doozy over here. Okay, so we have a few things going on. Let's go straight to the parentheses and let's deal with that. What is the inverse cosine of this value? So this is basically saying cosine, capital cosine x is equal to negative square root of 2 over 2. But we remember that x in this case has the distinction of having its domain values to be from 0 to pi. So the question is, what value of x is going to work here? And so from 0 to pi, when we get a cosine value of square root of 2 over 2, that is going to be at positive 3 pi over 4. So it's at a pi over 4. That's how we get the square root of 2 over 2. But the first pi over 4, we get a positive square root of 2 over 2. But at the next pi over 4 interval, let me go ahead and show what I'm talking about real quick. So instead of using the unit circle, I'm going to use the cosine curve real quick just to illustrate this. So we know the cosine curve starts up, comes down, and does one of these numbers. And this is halfway, so this is at pi. Right here, this is going to be at pi over 2 because we know that's going to be 0. And we have this value here, which is the square root of 2 over 2, and that's at pi over 4. And here at 3 pi over 4, we have, and I know this doesn't look pretty, negative square root of 2 over 2. Does that make sense? We could also do a similar thing if we look at the unit circle, but I figured let's go ahead and try something a little bit different here in terms of analyzing our situation. So from 0 to pi, we get that x value has to be at 3 pi over 4, at 3 pi over 4. So we got that. So this is 3 pi over 4. Now that that's taken care of, we're going to subtract 3 pi over 4 minus pi over 2 to get a pi over 4. Can you see it? I've got 3/4 minus 2/4. I'm left with 1/4. So this becomes the cosine of pi over 4. And the cosine of pi over 4 is simply the square root of 2 over 2. So for example 3, we are asked to determine if capital tan inverse of the tangent of x will be equal to x. Will that be true for all values of x? And if false, find a counterexample. And so if we look at this situation, guys, we know that these are two different functions, where this function is kind of like part of this function in a way. Not exactly. I know it's the inverse, but you get what I mean in terms of lowercase t. You can have any old value for x in here. You can literally use any value. But capital T, the capital T inverse, is only going to spit out some specific, remember, specific values that we talked about earlier, so that we can have an inverse function. So already there's some sense that this is not going to work out. So what I would do in this case is probably choose a number that's really large and see what happens. So in a way, we're considering, I just went over to Desmos. If you look at the red graph, that is our typical tangent function that's going to have a value for many of the values from negative infinity to positive infinity, of course, excluding those multiples of pi over 2 that are odd. However, we know that the capital tan, the inverse, is the inverse of this blue section right here. And that is only going to have specific finite values. So for instance, let's say we go back to our function and let 2 pi be the x value. So if 2 pi is that x value, the tangent of 2 pi, then we're going to do the tan inverse of whatever value we get there. Is that going to be x? The question is, will we get 2 pi? That's what we want to know. And the tangent of 2 pi is going to be 0. And then the inverse tan, remember the inverse tan is only pulling from a finite number of values. The inverse tan is going to put a square back at 0, right? Because we know that the tangent of 0, according to the capitalized function, that function that we were looking at over here, the tangent of the only 0 value we get along this portion of the graph, capital T, is going to be at 0 there. And so that's a contradiction already, and so we can see that that statement is false, and our contradiction is as such.